With the rise and application of artificial intelligence and machine learning across multiple industries, the civil and geotechnical engineering industry is not far behind. In this video, I want to discuss about the development and application of AI and machine learning in geotechnical engineering, the challenges, and what the future holds. This is Chido Chashe, and you are watching Geotechs with Clemens. Traditional methods in geotechnical engineering serve as the foundation bedrock for assessing subsurface conditions and mitigating risks associated with earth materials and man-made structures. Traditional engineering relies on mathematical formulations rooted in the fundamentals of soil and rock mechanics. A classic example is Tezagi's bearing capacity equations, which calculates the maximum load a soil can support based on factors like cohesion, unit weight, and internal friction angle. As for the slope stability assessment, practitioners traditionally use limit equilibrium methods to calculate the factor of safety. Many design parameters are calculated using correlations derived from regression fitting of historical datasets, often requiring expert judgment to apply correctly. As computational power increased, more sophisticated methods were integrated into the field. The finite element method and the finite difference method allowed for virtual assessment and analysis of complex geotechnical materials and structures such as tunnels and dams. This now could be done in a more cost-effective way. While instrumental to the field's success, traditional methods face significant challenges that have paved way for artificial intelligence and machine learning integration. You see, soil is a three-phase system that is inherently anisotropic and heterogeneous. Traditional models often simplify these into non-linear relationships, which may fail to capture the ground's true and messy reality. Many empirical models are derived from specific geographic regions and may not apply accurately to sites with different geological histories. Furthermore, extensive lab and field testings are resource-intensive and expensive, and can delay construction projects in the end. Research on artificial intelligence and machine learning in geotechnical engineering is not a recent phenomenon. The history spans more than 3 decades, evolving from early simple systems to sophisticated data-driven deep learning models. The early systems back in the 1980s focused on replicating human decision-making using mathematical, statistical, and logical concepts. Then, the early 90s marked the emergence of artificial neural networks as a transformative tool in geotechnics. In 1992, Lee and Sterling published the first study using artificial intelligence to predict failure modes in open pits. Around the same time, researchers began using artificial neural networks for site characterization and predicting the bearing capacity of foundations. The first decade of the 21st century saw a sharp increase in the variety of algorithms and their application areas. Beyond artificial neural networks, researchers began adopting support vector machines, decision trees, and fuzzy inference systems. The application of AI-based predictions in landslide susceptibility mapping and soil liquefaction assessment became prominent in the early 2000s. Around the same time, tunneling and tunnel boring machine performance modeling gained momentum, helping engineers to optimize tunnel alignment and ground improvement techniques. The last decade has witnessed an exponential growth in geotechnical AI research, driven by increased computational power and the advent of big data. Deep learning algorithms such as convolutional neural networks for image recognition and recurrent neural networks for time series data have become state-of-the-art. While only a handful of articles were published annually in the early 2000s, by 2019, there were over 43 major publications focusing on deep learning in geotechnics. However, throughout this period, artificial neural networks remain the most widely used technique, involved in 52 to 80% of all studies across various geotechnical subdisciplines. So now that we have touched on the history and the evolution of artificial intelligence and machine learning in geotechnical engineering, how do these machine learning models work? Machine learning algorithms work as a data-driven approach that enables computers to learn from existing data to make predictions or decisions without being explicitly programmed for the specific task. Unlike traditional physics-based models that rely on established physical laws, machine learning models capture complex functional relationships directly from data, even when the underlying physical principles are unknown or difficult to explain. A good example is predicting ground surface settlement during tunneling with a tunnel boring machine. During the supervised training of the model, you feed the model multiple input variables such as tunnel boring machine penetration rate, the thrusts, the grouting ratio, and the like, along with the associated measured ground settlements. The model then learns the relationship between the input variables and the output without explicitly giving the model a function. Generally, machine learning algorithms follow 4 steps during training. Before an algorithm can learn, the data must be made neat and uniform. This includes identifying and eliminating outlier data points that could skew the model's accuracy, standardizing numerical data to a common scale to ensure the model treats all features fairly and doesn't overvalue one variable simply because it has large raw numbers. The dataset is then split into a training dataset to build the model and a testing set to evaluate its performance on unseen data. The core of machine learning is the iterative process of training, where the model adjusts its internal parameters to minimize the error between its predictions and actual historical outcomes. In artificial neural networks, inputs are multiplied by adjustable weights and added to a bias or threshold. The resulting signal is passed through a nonlinear algebraic function to produce an output. This allows the model to handle messy, nonlinear real-world relationships. The model then calculates its own error and uses this error to work backward through the model, updating weights and biases to improve the next prediction. In the last section, I touched on the learning mechanics of machine learning algorithms. I spoke about parameters such as weights, which the model configures during training. However, there is another external configuration called the hyperparameter tuning, which is set by the engineer or the data scientist in combination with the machine learning algorithm before the training process. These are often fine-tuned optimization algorithms that find the most effective parameter settings for a specific problem. A good example is the particle swarm optimization algorithm, an algorithm inspired by the social behavior of bird swarms searching for an optimum location, such as a resting place. In the simplest terms, here's how it works. The algorithm looks at a group of potential solutions, treating each one like a single bird or a particle. Each particle starts at a random position and then moves through the search space with a specific velocity. Every particle remembers 2 things to decide where to move next: personal best, that is, the best solution it has found on its own so far, and the global best, which is the best solution found by any member of the entire group. By constantly adjusting their speed and direction towards the best points, the entire group eventually clusters around the most accurate solution. These optimized parameters are then fed into the model for a more accurate result. To ensure that the machine learning model isn't just memorizing the training data, a problem called overfitting, a technique like k-fold cross-validation is implemented. This involves splitting the data into k subsets and rotating which subset is used for validation while training on the others. A successful model demonstrates high accuracy on the independent testing set, proving it can generalize its knowledge to new scenarios. Not all machine learning models have the same architecture and functions the same. Some algorithms are best for classification and others are well suited for regression. Here are some of the most commonly used models in the industry and in research. We have the artificial neural networks. These are the most widely utilized AI techniques, involved in over 51% of the published geotechnical studies. They mimic human behavior to approximate complex functions and recognize patterns. They are best used in power foundation design, where they can predict the friction capacity and end-bearing capacity of piles more accurately than traditional empirical methods. They are also used in the foundation settlement area, where they can estimate the settlement of shallow and deep foundations in various soil types. They are also good at correlating soil and rock parameters such as relative density, shear strength, and unconfined compressive strength. As of late, artificial neural networks are being used to evaluate the potential for soil liquefaction during seismic events. Random forests is an ensemble learning method that combines multiple decision trees to improve accuracy and resist overfitting. They are frequently recommended as the superior method for identifying soil types based on cone penetration test data, predicting indices like maximum dry density, optimal moisture content, and the California bearing ratio. They are highly effective at predicting shear wave velocity using minimal input features from CPT soundings. Moreover, they can generate precise maps to assess the likelihood of slope failure. Support vector machines are effective for classification and regression, particularly when dealing with high-dimensional data and small sample sizes. Best used in rock classification and deformation, landslide susceptibility mapping, and categorizing soils based on their bearing capacity or liquefaction potential. Deep learning uses multi-layered neural networks to extract high-level features from large, complex datasets. We have convolutional neural networks, best used in image-based tasks such as rock image identification, detecting cracks in tunnel linings, and classifying geological features from field photos. There are recurrent neural networks and LSTMs, which are best used for time series problems, where memory of previous states is required, such as forecasting landslide displacements over time or predicting tunnel boring machine performance during tunneling. Lastly, we have the generative adversarial networks. These are best at synthesizing synthetic soil profiles, which helps engineers simulate underground conditions in regions where physical sampling data is scarce. AI and machine learning models have been implemented in numerous real-world geotechnical projects globally, ranging from hazard mitigation and disaster response to optimizing large-scale construction processes. Long short-term memory models were deployed to forecast periodic displacements of the Baishwehwe and Banzimen landslides around the Three Gorges Reservoir area in China. These models accurately predicted movements triggered by rainfall and reservoir water changes. In the Swiss Alps during the construction of the new railway tunnel, machine learning models were used to analyze real-time data from drilling machine sensors to predict unstable soil layers and water ingress. This allowed engineers to adjust drilling strategies instantly and prevent cave-ins. A Bayesian-optimized long short-term memory model was similarly implemented to predict the advancement rates of a dual-mode shield tunneling in complex strata during the construction of the Shenzhen Metro Line 13 in China. The model maintained an 80% accuracy even in challenging geological conditions, showing the predictability potential of these machine learning models. These are just a few examples of where the industry is at when it comes to the implementation and utilization of AI in practice. Large language models, or LLMs, like GPT-4 and other specialized frameworks are being used to revolutionize human algorithm interaction in geotechnical practice. LLMs are being used to draft ground investigation reports and automate intelligent geotechnical design workflows. Early feasibility studies indicate that general LLMs can answer textbook-level geotechnical questions with an approximate 70% accuracy, though they are still faced with challenges like hallucination and spurious reasoning. Specialized models like GeoLLM are being introduced. These are specialized models fine-tuned for niche geotechnical design and complex query handling. Other techniques such as retrieval augmented generation and few-shot learning are also being employed on LLM outputs to enhance their reliability. Despite AI's potential, there are still several formidable obstacles hindering the transition from research to widespread industrial adoption. You see, AI requires quality data for training. Sparse, noisy, or unrepresentative data leads to the garbage in is equals to garbage out problem. One of the most challenging aspects as well is the black box problem. Many complex algorithms, particularly deep neural networks, lack interpretability. To put it in simple terms, we actually really don't know how some of these algorithms compute, and as engineers, we often hesitate to trust models that cannot provide a clear cause and effect relationship or explain the why behind the prediction. There are other concerns like in generalization and extrapolation. You see, many models are site-specific and exhibit poor generalization when applied to different soil types or geological conditions outside the range of their training data. There is the ethical and legal side of things. There are questions regarding accountability in the case that an AI prediction leads to failure, as well as concerns over clients' data protection, meaning to say, can we use our clients' data to train our internal models? Who knows? In conclusion, while AI and machine learning have already demonstrated the ability to match or surpass traditional methods in specific tasks, the future of geotechnical engineering will rely on the multidisciplinary approach where the engineer remains in the loop using AI as an advanced tool to augment human experience and judgment. If you found this interesting, please like the video and subscribe to the channel. I will see you on the next one. Cheers.